says that has to be down. True.
I will begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. I thank you for these students and just ask you to bless our work today, Lord. In your name I pray. Amen. So, just a couple of calculations with power series. So at the moment, I'm almost done with our discussion of how to manipulate power series via the geometric series technique, right? How to find interval of convergence, radius of convergence. Mostly we've just looked at how to find the domain of a power series. We have not yet explored the question of how does a power series generally represent a function. I mean, we're getting close to it. We've seen some examples of it. We haven't yet seen Taylor's theorem. But there's one theorem I want to share with you before we get to that, which is just this theorem. If f of x is the sum Cn x minus x naught to the n, and g of x is equal to the sum n equals 0 to infinity of, say, bn, x minus x naught to the n, then number one, f of x times g of x can be written as the sum over, let's say, dn x minus x naught to the n equals 0 to infinity, all right? And two, provided b sub 0 is not equal to 0, f of x over g of x is also can be expressed as the sum n equals 0 to infinity of some dn x minus. Obviously not the same d for part 1 and 2 here, all right? So what I'm trying to say in this theorem is that if you have two power series centered at x naught, you can multiply them to get a new power series centered at x naught, and you can even divide them to find a new power series centered at x naught, provided that the power series that you're dividing by has a zeroth, a constant coefficient being non-zero. If the constant coefficient is 0, it may still be possible to divide, but then there's some kind of extra strings attached and customs that we have to discuss. All right. Now, I'd rather not try to describe to you what dn is, generally speaking, for arbitrary series, because I could do that, but it would give you the wrong impression. You might be tempted then to use those formulas to multiply series. That's really not what I want. It's not what you want either. To multiply series or to divide series, you just do the same as you've already done with polynomials, being careful to keep track of the calculations order by order. All right? So let me just do a couple of examples. So let's suppose we had 1 plus 2x plus 3x squared plus 4x cubed plus dot, 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 dot. I'm going to take that series, and I'm going to multiply that power series by, let's say, 1 minus x cubed plus 2x to the 6th plus, well, this is too much. I've gotten carried away again. Let's say 1 minus x plus 2x squared minus 3x cubed plus dot, dot, dot there. All right. So what I want to do is I want to multiply these series. All right. up to, let's say, third order. So the way to do this is just to go order by order, all right, making sure that you don't miss anything as you think about distributing the terms, right? So we start with the constant terms. What's the constant term? 1, right. So we get 1, because 1 times 1 is 1. And then sometimes I put the x first, and then put the coefficients second, because it's just, that's how I think, right? But I don't usually leave it like this, because it's kind of tacky to put the number after the x. I don't know, it's just bad form. So how do I get x's? 1 times this minus x gives me a minus 1, right? But also, 2x times 1, so I get minus 1 plus 2, yeah? See that? Are there any other ways to get x? I don't think so. So next up, x squared, all right? So x squared, we can do 1 times 2x squared, so I get a 2, right? Again, then I have 2x times minus x, that gives me a minus 2x squared, right? And then finally, plus 3x squared, so I get a plus 3. So this 3 is coming from this times that. This 2 is coming from this guy times this guy. And this 2 is coming from this times that. All right? You just got to be careful to be consistent and not to miss anything. Right? Just like regular multiplication of polynomials, right? Which you guys are already really good at, so this should be not a big deal, right? What's next? Order 3, right? This is the end of the road because of my problem statement that I just erased. So x cubed. Keeping with my pattern, I'll start with 1 times, I get a minus 3, plus 4, minus 3, and then finally plus 4 again. So what's the answer? Multiplying these series gives us 1 plus x plus 3x squared plus 2x cubed, yeah? And that is how you multiply series. Does that make sense? Okay. Now, dividing series, now that might be a little bit, here I'm probably going to have to, this may be a little bit more of a shock to you. Example 2. So let me show you 2 different ways to divide series, all right? So if I'm looking for, suppose I want to calculate 1 over 1 minus 1/2 x squared plus 1 over 24 x to the 4th minus 1 over 120 x to the, did I get that right? Yeah, x to the 6th. Right? Suppose I want to find the reciprocal, all right, of that series. Like, what's 1 over that series? First of all, the theorem gives me hope because my b sub 0 is what? Let's go to third order. So here's an idea. If you think about what we're looking for, right? We're looking for something, what, like basically A0, let me say D0 plus D1x plus D2x squared plus D3x cubed plus dot, 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 dot. I mean, my goal is to figure out what D sub 0, D sub 1, D sub 2, and D sub 3 are, right? So one way you could attack this problem would be to think about solving what? So we could just solve 1 equals to the product of 1 minus 1 half x squared plus 1 over 24x to the fourth. And I think that's probably all I need, yeah? That times d0 plus d1x plus d2x squared plus d3x cubed plus dot, 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 right? If I could figure out what values I need for d0, d1, d2, and d3, I would have solved the problem, right? Our goal is to find numbers for d0, d1, d2, and d3, okay? One of the things I've failed to emphasize with you guys up to this point, but it's just kind of, well, maybe I even used it already, but it's something that should be said, is when we have two power series, right, and we know that they're equal, that says things about their relation. It says that they have to have, well, you guys tell me, if I had 3x squared plus 2x minus 7, and I said that was equal to ax squared plus bx plus c, what's a, b, and c? 3, 2, and minus 7, right? You don't even think about it, right? You just know that that's true. Why? Somebody told you in middle school, right? Why is it true, though? Plug in 0. What do you get? Minus 7 equals to c. Differentiate the expression. What do you get? So if we differentiate the expression, we get, you know what? We get 2. Instead, we get 2 equals to b, right? If we look at the second derivative and feed that, well, you don't even need to feed it 0. Just look at the second derivative. On the left-hand side, you get 6. On the right-hand side, you get 2a, right? I'm sorry, you get, is that right? Yeah, 2a. And so there you go. A equals 3. B equals 2, C equals minus 7. We can derive that by evaluation at 0, and then differentiation and evaluation, and then differentiation and evaluation, right? We can kind of work our way from the constant coefficients all the way up the chain by systematic evaluation / differentiation, right? We can show that the coefficients of a polynomial have to match if they're equal. The same is true for power series. Two power series are only going to be equal if they match term by term. That's very useful here because, well, on the left-hand side, the coefficients are all 0 except for the constant term, right? On the right-hand side, we can multiply them out, right? And so, like, multiplying this out gives us what? D0 plus x times what? D1, right? Well, I'll just write it this way. D1x plus, what are the coefficients for x squared? Minus 1/2 D0, right? Minus 1/2 D0, and where else can I get an x squared from? Oh, how about 1 times D, so plus D2, yeah? See what I did there? So what I'm saying is this is coming from this times that, and then this one times that one gives me the d2. And that's the only possible ways I can get an x squared from multiplying terms in the left and right factors that I'm multiplying. Do you agree? How else would I might be able to get it from x times x, except I can't do that because what? There's no x term in here, right? Except the one that's 0. And then x cubed, what we got? We've got d3, and it looks like minus 1/2 d1, and I think that's it. So one way we can look at reciprocating a series is it's the problem of solving a bunch of equations, right? It's a bunch of equations, one for each coefficient. What are the equations I need to solve? So the reason I talked about the quadratic over here for just a second is to draw your attention to the fact that we equate coefficients. We equate coefficients of like powers. Same true for power series. Equating the constant term here. So constants, what does it give me? 1 equals to d0, yeah? Hey, well that one wasn't bad, right? And then how about x? Equating coefficients of x, what do we got? We got 0 equals to, what is it? d1. Well, that was also a pretty easy equation to solve, right? X squared. By the way, if you look at the expression that we're finding the reciprocal of, it's an even function, right? Do you guys remember what even function means? F of minus x is equal to f of x. So we're looking at the reciprocal of an even function, which is, by the way, I would say an even series. It's formed from even powers of x, right? Is the reciprocal of an even function an even function? Search your heart. You'll find it to be true. And if you believe me that power series the power series which represents an even function should be an even series, this is not surprising that we found that the odd term is 0. In fact, I expect that d1 is 0, d3 is 0. If we were to keep going, d5 would be 0. It's only the even terms which are going to be non-trivial, because this is an even function which has an even series. This is a very helpful comment I'm making as you work problems, all right? You can see whether you're going right or wrong in part if you follow this guide. Many problems you work with are either even or odd. Okay, anyway, x squared, we got what? We got 0 equal to minus 1/2 d0 plus d2, which tells me that d2 is 1/2 d0, which means that d2 is 1/2. And then x cubed, we get 0 is equal to d3 minus 1/2 d1, which implies that d3 is equal to 0. Right? So we did it. We did it. What's the reciprocal? In summary, one over 1 minus 1/2 x squared plus 1 over, 4 factorial, but I'll write it as 24, x to the 4th plus dot, 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 is equal to, well, 1 plus 1/2 x squared. That's all we got at the moment. That is up to order 3. Up to and including would be a better, up to and including order 3. Just to be clear. Now, this is a relatively straightforward process, but there's like a shortcut. There's an easier algorithm for finding the reciprocal of a series, and I should share that with you now. So let's look at this example. I'll look at it in example 3. All right. In example 3, we're going to look at oh, sorry, I was trying to be clever. Don't be clever. That is my default, not being clever. Fine. 1 over 1 minus. Oh, if I'm clever here, you won't be able to see what we're doing. I better not. Don't be an idiot. It's not worth the joke. Let me just show you the method. So I'll actually rework this example. So another way we could have done the previous example just directly would be to use long division. Long division makes sense for series if you're just careful. And so what are we doing? We are dividing 1. You put 1 here. We put the thing where, I think we put that over there. For those of you who have forgotten long division, if we're going to do 375 divided by 8, how does that go? We put the 375 up here, in here, right? We put the 8 over here, and then we go to town, right? So we got a 4, that gives us a 32. We subtract, that gives us 55. That gives us what? Seven? No. 6. 48, that gives us a 7. 7 is smaller than the 8, that's the remainder. This tells us that that 375 divided by 8 is equal to 46 plus remainder 7 divided by 8, right? This is long division. So with that in mind, can you fix what I did? How should we start? Have I started the right way? I have not. And there's an easy way to figure out if you've started the right way or the wrong way, which is what? Remind yourself how long division works and think about the analogy, right? It's not hard. So what should go where? If I'm trying to calculate 1 divided by that series. 1 goes in the inside, right? And the thing I'm dividing by, the series, goes on the outside. Can you guys tell me what these are called? What's the thing you're dividing by? Does it have a name? Oh, 1/24, thank you. It is the divisor, yes? So, although that, well, anyway, let us refer to it as the thing we're dividing by to avoid trouble. So to start with, looks like I need a 1, right? So I take 1 times this, it gives me 1 minus 1/2 x squared plus 1 over 24 x to the 4th, right? I take the difference, that gives me 1/2 x squared minus 1 over 24 x to the 4th, right? And then, so I need a plus a half x squared up here. But then we have to think about 1/2 x squared, right? This 1/2 x squared times that gives me what? It gives me 1/2 x squared minus 1/4 x to the 4th, yeah? Agree? But then long division says take the difference of the black and the red. That gives us blue. Upcoming blue. Where'd my blue? Thinking of something blue. So 1/24 minus 6/24 is otherwise known as 5/24, yes. All right, so 5/24 x to the 4th plus dot, 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 dot. All right. It's easy enough to see that the next term I put in the numerator is plus 5/24 x to the 4th. Yep. Well, I have minus 1/24 plus 6/24. So I agree with what you said, yes. Hey, look at that. We just found the next term that we didn't find in my previous calculational method with what? I would say a lot less work. So long division of series, this is a useful calculational technique if you just want to find the first few terms in the reciprocal series. All right? We good? I hope so. Now, let me confess what we're looking at. We will soon learn, by the way, that cosine of x can be represented as 1 minus 1/2 x squared plus 1/24 x to the 4th plus dot, 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 dot. So that is, in fact, the so-called Maclaurin series for cosine. We will soon derive this. I'm just telling you the meaning of this example before I forget to tell you. So what if we just derived in examples 2 and 3? Yeah, we found that is so what we're looking at here is actually the power series expansion of secant x. Well, the first 3 non-trivial terms in the power series for secant x. All right? Okay. So, at this point, it's time for us to have the talk. It's time for us to grow up. And by that, I mean we need to look at, well, before we do mature things, let's do something immature. 69, 79. There you go. So I need to take you guys down. Let me tell you what we're about to do. We're about to take a hard look at Taylor's theorem. All right, what does Taylor's theorem say? Well, here's a slogan. This is what we want to understand in after the next discussion. On the interval of convergence, a power series is the Taylor series of its sum. All right, let me elaborate on this. Suppose we have f of x equals to C0 plus C1 x minus x naught plus C2 x minus x naught squared plus dot, 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 dot. Okay? This is the quote-unquote sum. This, of course, is the power series. All right? What is this Taylor series? What is the Taylor series? The Taylor series of its sum. Taylor series of its sum. What's this mean? This means we start with f of x, and we do something to generate a series from f of x. And so I'll just tell you what that is. The Taylor series of its sum actually is t, let's say, I'll say t sub f of x for Taylor series of f. And that's going to be f of x naught plus f prime of x naught times x minus x naught plus 1/2 f prime prime of x naught x minus x naught squared. To be more complete, tf of x will be equal to, and I want to explain why this is, the sum n equals 0 to infinity of the nth derivative, rather, evaluated at x naught, divided by n factorial times x minus x naught to the n. This is the full Taylor series for f. All right? I'll work it out over here. So let's begin as Lagrange began when he wrote his calculus book in the late 18th century. He said, imagine a function. You know, what's a function? Well, to Lagrange, a function was a power series. Like, that's how his book starts. He says something like, imagine f of x equals to c0 plus c1x plus c2x squared plus dot, 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 dot. For the sake of reducing clutter, I'm going to put x0 equal to 0 in this discussion over here, all right? Everything I'm doing at x0 equal to 0 could easily be written down as I have on the right board. All right? So I'm going to set x sub 0 equals to 0 for brevity, and to try to make your note writing experience a little less painful. All right? So, what's the deal? What is f prime of x equal to? Remember, we've talked about this. You differentiate a series term by term, right? So what's the derivative of the series? c1 plus 2c2x plus 3c3 x squared plus 4c4 x cubed. I'll just go that far. Right? So what's the second derivative of the series? Aha, well now it's 2c2 plus 6, I'll write it as 3 times 2. 3 times 2 c3x plus 4 times 3 c4 x squared, right? And so what happens if I differentiate again? What's the third derivative? F prime 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 Well, the 2c2 goes away, and we're left with 3 times 2 times c3 plus 4 times 3 times 2 c4x, right? So in polite company, it's customary to write this as f of parentheses 4 of x, right? But if you really like the prime notation, you could still be like f prime 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 of x. I don't recommend that, though. So f parentheses 4 means the fourth derivative, right? And so that gives us 4 times 3 times 2 times, well, c4, and then plus, well, what's the next term? It's 5 times 4 times 3 times 2 c5x for what it's worth, right? What happens if we keep doing this? Like, what's the derivative? What's the, let's say, the nth derivative of x? What's that look like? It's n times n minus 1 all the way times 3 times 2 times cn plus stuff, right? And so, in fact, if you look, just look at what we've done, what happens when we evaluate? What happens when we evaluate any of these at 0? Do you see? F of 0, also known, by the way, as f parentheses 0 of 0, is c0. F prime of 0, also known as f parentheses 1 of 0, is c1. F prime prime of 0 is, I'm getting sick of writing this, is 2c2, right? F prime 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 of 0 is, well, it's 3 factorial c3, isn't it? And f, the fourth derivative at 0, you know what it is? It's 4 factorial c4. In retrospect, this was 0 factorial times c0. This was 1 factorial times c1. This was 2 factorial times c2. It's always n factorial times cn, in fact. So generically speaking, the nth derivative evaluated at 0 is equal to cn times, well, n factorial times cn. If I start with the assumption that my function is a power series, all right, that means that the function is in fact infinitely differentiable. I can keep taking derivatives until the cows come home, right? There's always another one to take. And who says that? A bunch of farmers, I guess. I don't know. I don't really have the life experience to use that phrase. I really shouldn't. I mean, it's very insensitive of me to think about it. I mean, but anyway, so if the function is given by a power series, it can be differentiated, and there is a connection between the coefficients of the power series and the derivatives of the function and its higher derivatives and the function itself evaluated at the center of the series, right? You see what we have? We have that f of x is equal to a sum n equals 0 to infinity of, well, the nth derivative at 0 over n factorial times x to the n. Because this says that cn is the nth derivative at 0 divided by n factorial, right? So let me repeat the logic again. If the function has a power series representation, write that down. If f of x has power series representation, right? then Cn is going to be equal to the nth derivative at x naught divided by n factorial for n equals to 0, 1, 2, all the way on out. But this is an if-then statement. I'm assuming at the start that there exists a power series that represents the function. Okay? And do you see that? I mean, I wrote the calculation in purple for 0, but you believe me that we could easily replace all of the x's with x minus x naught to a power, and the same calculation would go through, right? You don't want me to write that out, though, do you? I don't want to write it out. Okay? So anytime I try to draw your attention to like an if-then, what does that suggest? Maybe there's some kind of like possibility that this doesn't happen, right? So let me show you the example which kept 19th century mathematicians up at night. This is a very troubling example because it defies the imagination of Lagrange, and that that's not an easy thing to do. So there's a function, and this function's smooth, very smooth, and it's 0, like these, and then it comes into the origin, and it's just so smooth. It just goes up like that, and then eventually it kind of tableaus out here at 1. The function is this: f of x equals to 0 for x less than or equal to 0, and exponential of minus 1 over x squared for x positive. All right, notice that the exponential of minus 1 over x squared, that has trouble at x equals to 0, right? There's something nefarious happening there. But at the same time, it's not so bad either, right? As x approaches 0 from the right, what happens to x squared? It's super small, right? But what's e to, so the reciprocal gets what? You think about the limit as x goes to 0 from the right. This is going to what? Like e to the minus infinity, which is going to 0. So the fact that these two cases glue together continuously at 0, it's not hard to believe. If, right, this was a 400 level real analysis class, maybe I'd make you prove that not only is this function continuous at the origin, but in fact its derivatives at 0 exist to arbitrary order. You can prove, you can show that the nth derivative at 0 for this function, so defined, is equal to 0 for all n. Right? So here is a function, all right, which has zeros, is derivative 0 not just the first, not the second, not the third, but all of the derivatives are 0 at 0. So here's the thought process. You have your Taylor series generator. So the Taylor series generator, what does it do? It takes in f of x, all right? And this is at x0 equal to 0. All right, so you could call this the Maclaurin series generator. So the Taylor series generator, what does it do? It takes in a function, right? Now, in order to not to give the Taylor series generator indigestion, you need to make sure you're giving it a function which is smooth. What's smooth mean? We say a function is smooth. Well, in fact, this function's everywhere smooth. That means that the derivatives, the second derivatives, the third derivatives, arbitrary derivatives of the function exist and are continuous. This is a smooth function. The function I have graphed up there is a smooth function. So anytime you have a smooth function, right? If we have a smooth function, we can calculate the Taylor series of it. What is the Taylor series? Output is the sum n equals 0 to infinity, the nth derivative of f at 0 divided by n factorial times x to the n. All right, this is the Taylor series for f at x. I'm calling that T sub f of x for Taylor series of f. All right? Are these equal? What is the Taylor series for this function? Yeah, the Taylor series for this function is 0. Is this function 0? No, it is not 0, right? So in other words, for this rather annoying function, f of x is not equal to the Taylor series for f of x. A function which is not represented by its Taylor series at a point, all right, is said to be non-analytic. So f of x is not analytic. At x not equal to 0. If you take this function anywhere except for x equals to 0, in fact, locally, the function will be represented by its Taylor series. It's just this one trouble spot for this function. At 0, it's not analytic. So what does analytic mean? Analytic, this is a definition, f of x is analytic at x naught if there exists neighborhood of x naught on which f of x is equal to the Taylor series for f of x for all x in the neighborhood. NB, this is my stupid abbreviation for neighborhood, as in like, won't you be my neighbor? All right. Now, so in other words, what I'm trying to say is what Lagrange said at the start of his calculus book is, suppose we're looking at an analytic function. What's an, and this is also, to be more precise, this is real analytic. All right, real analytic. So good news, guys, is that most of the functions that we're interested in for applications, in fact, are analytic functions, which means that the power series that is given to us by Taylor's, the Taylor series generating machine, in fact, represents the function. Okay? So how can you be sure that a function is represented by its Taylor series? Like what theorem tells you how to judge whether or not this is true? Taylor's theorem, of course. So let's look at that. Now this so I'd like you to understand the proof I'm about to go over, the big picture of it. This is not something I expect you to replicate on the next test. You'll see why soon enough. Part of the reason is I really feel like this is a Calculus 1 topic. You're like, what? What do you mean this is a Calculus 1 topic? Well, if you really look at what we're doing, we are, I mean, well, I'm waiting for this thing to load up, which is going to be a long time if I don't plug it in. Come on. Make up. Look at this. What is this? If I say y equals to f of x naught plus f prime of x naught times x minus x naught, what's the significance of that? Yeah, that's the tangent line. So that's the tangent line. So this is what I call T1 of x. This is the first Taylor polynomial, the first order Taylor polynomial of x. All right? T0 of x is just f of x naught. All right? So in fact, when I teach Calculus 1, I cover this. Because what it is the discussion of how do you take a function and represent it with a polynomial approximation, right? And I just feel bad in Calculus 1 to stop at tangent lines when it's almost the same discussion to go on to, like, what's the best quadratic approximation, what's the best cubic approximation, and so forth. So they don't let me teach Calculus 1 for some reason. Just kidding. It's just a problem of scheduling. It's not that. But this is my chapter 6. And so to understand the proof I'm going to show you, we need to take a step back down memory lane here, because at the heart of all this is Rolle's theorem. All right. Now you may or may not remember what Rolle's theorem says. Let's go to it. Actually, before we can even do Rolle's theorem, we need to remind ourselves, what's the extreme value theorem say? The extreme value theorem says if you got a function which is continuous, ooh, whoa. Maybe a bit much. I need to find like a more mellow green laser. I like green, but my green lasers are always like crazy bright. So if we have a function which is continuous on a closed interval, it attains its absolute maximum f of c somewhere in there, right? This is the extreme value theorem. If you take a hard look at this, it actually involves the that completeness axiom for the real numbers, that least upper bound property that comes into play here. That's in the details. But I don't even show them in my notes. This is actually something that you probably can't prove with calculus alone. This is actually a topological result, whatever topology is. Topology is the study of open and closed and continuity in more general. Topology is the study of continuity in the abstract. Anyway, that's the extreme value theorem. So then, of course, we introduced the concept of a critical point, which was where a derivative was 0, right? Remember that? We had Fabre's theorem. May or may not have proved anything. Eventually, we get to Rolle's theorem. What did Rolle's theorem say? Rolle's theorem said, if you have a function that's continuous on the closed interval, differentiable on the open interval, and starts and stops at the same point, that means somewhere in the motion of the laser there was a place where it had velocity 0, right? Because the initial and final y positions were the same, so somewhere there's a y velocity 0 in that motion, right? That's Rolle's theorem. There exists a c such that f prime of c is equal to 0. Now, if you look at the proof here, I just wanted to point out to you, it's really just an application of the extreme value theorem. If you get into the details here, the reason that we know that's true is because of the extreme value theorem. Now, moving on, once you know Rolle's theorem, you're able to prove the mean value theorem. And the mean value theorem says that it says that the average rate of change is equal to the instantaneous rate of change somewhere in the interval. That's one way to look at it. If I think about x as being time, this would be the velocity at time c. This would be the average velocity if we think about f being position and x being time. But mean value theorem said I need a continuous function on the closed interval, and I need the function to be differentiable on the open interval. All right? Then there exists this c such that the f prime of c is equal to that. In other words, f of b minus f of a is equal to f prime c times b minus a for some c. The way you prove this is by applying Rolle's theorem to the secant line. What's the secant line? The secant line is the line that has slope that's equal to the average rate of change, and it's centered at a, comma f of a for what it's worth, all right? So you look at the secant, this function, the graph of this function is the secant line, all right? And actually, I don't look at that directly. That's not what I apply. Actually, it's been about 5 years since I taught Calc 1, so forgive me. But you actually take this and take the difference of the secant line and f of x. That's what we apply Rolle's theorem to, because the difference of f of x and the secant line is such that when you plug in the a and b, you get 0, which means somewhere in the middle, there has to exist a c such that h prime of c is equal to 0, but h prime of c being 0 is tantamount to there existing the point that we need c for the mean value theorem, all right? But the larger thing I wanted you to see from here is the proof of the mean value theorem really is using Rolle's theorem for the secant line, slightly perturbed. The reason I want to go through this is so that the proof I show you next doesn't seem so mysterious, all right? We skip ahead to page 197. So it's going to be a couple minutes before I get back to the actual proof of Taylor's theorem. I just have a little bit more preparation to show you. I wanted to actually show you some examples of Taylor polynomials for specific functions before we get back to the proof, okay? So bear with me. These calculations we just went through, in some sense, you know, what's the difference between the calculations in this section and what I had on the board over here? There's one significant difference. Here, I'm not starting with a power series. I'm starting with a function that's somehow given, all right? And then we're deriving things that should be true for that function if it's a smooth function, okay? So I work out that if you were to look at, you know, the approximation of the function at second or third order, we, of course, can approximate the function by using the kth Taylor polynomial, which is, you know, f of a. So the first two terms are the, you know, the tangent line. This is the best quadratic approximation to the function. This would be the best kth order polynomial approximation to f of x, all right? But don't take my word for it. Let's actually look at some. F of x equals e to the x, all right? So I can calculate the 0th, 1st, 2nd, and 3rd Taylor polynomials for e to the x centered at -1, all right? So this is f of -1 is 1 over e, right? E to the -1 is 1 over e. What's the derivative of e to the x for arbitrary order? E to the x, right? So all of the stupid fn of zeros, excuse me, fn of -1 is always 1 over e for this example, which is why I've got like 1 over e, 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 1 over e. What's this 1/6? That's the 1 over 3 factorial. That 2 is the 1 over 2 factorial that we've derived in the purple, remember? Here's a picture. So what you're looking at, the dotted red line is the actual graph of the exponential. The blue is the tangent line to the exponential through -1. The green is the best quadratic that fits through -1. The purple is the best cubic that fits through -1. As you can see, as you go higher and higher Taylor polynomials, we're staying closer and closer to the function we're approximating, e to the x, right? How close, though? How good is the approximation? Here's another one. I can find the first few Taylor polynomials centered at 1 for this function, all right? And so I differentiate, 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 and then I'm going to plug in 1 and see what happens.